All right, let's practice some proofs. I just made up some of these problems and they use some of my favorite reasons along with some of your suggestions. One of the first things I saw was somebody suggested me talking more about the right angles congruence theorem. We know that the right angles congruence theorem says that right angles are congruent to each other, but why would you need to use that? When do you need to use that? Well, let's try this one and see if we need it in this one. You can see that I'm given congruent angles, but then I'm given right angles. And I can't put a little a out there because it doesn't say that they're congruent. So if I wanted to use that as a set of congruent angles, I would need to use the right angles congruence theorem. I haven't decided yet if I want to use those angles as congruent angles, because sometimes when you have right angles, you want to use HL. So let's see what else I can see on the picture. I see that we have shared sides here. I can see that I have BD congruent to BD by the reflexive property. That's a set of congruent sides. And it looks like I'm going to need one more thing, right? And this can't be hypotenuse leg because there's no way to tell if those hypotenuses are congruent to each other. So I do think I would like to use those right angles as congruent angles, using that as my third set of congruent pieces. And so to answer your question, we're going to use the right angles congruence theorem when we want to use a pair of right angles just as a random set of congruent angles. When we want to use those right angles as right triangles on a hypotenuse leg proof, then we wouldn't need to use the right angles congruence theorem. I've got two angles in one side. Let's look at the picture. It looks like we've got an angle and the side that's not between them. So that's angle, angle, side, congruence. This one's a theorem, I think. I don't care if you get that wrong. If you say postulate when you mean theorem, I'm really just looking for the order of those letters. And have we noticed that the triangles are congruent? The reason that goes with that is always one of those 3 letters or 2 letters in the case of HL, one of those triangle congruence postulates. Remember, there's 5 choices when we're trying to prove that triangles are congruent to each other. I had another request that I talk about some parallel line reasons. First thing I have to do on this one, I see 2 triangles, but they're sharing a side, so I'm going to say that BD is congruent to BD by the reflexive property. I'll always take those easy points of shared sides or bow tie vertical angles every time. Let's see what we have so far. We've got a set of congruent angles that was given. We found ourselves a set of congruent sides, and I was given some parallel lines. One common mistake is that people will say that that's a set of sides. Now, although it is a set of sides, they are not congruent to each other. At least I don't know if they're the same length. All I know is that they're parallel to each other. So I'm going to be looking for either corresponding or alternate interior are the 2 common ones. So I know that I'm either looking for that sort of Z shape, or I'd be looking for maybe some corresponding angles. And when you step back, doesn't this look like one of those classic Z shapes using the parallel lines that I talk about? So if you can find that sort of formation, then you know that you can mark those alternate interior angles congruent. So one thing to look for if you have parallel lines is to see if you can make a sort of Z shape. Maybe you even want to write a note to yourself on your pink reasons sheet. Just put a Z next to that theorem to remind you you could be looking for a backwards N or a backwards Z or some variation of that. But as long as you have those parallel lines, you'd be finding those alternate interior angles congruent. That gave me a third set of congruent parts. So that means I'm ready to say that those triangles are congruent using one of those 3-letter congruence postulates or theorems. I have to look back at the picture again to see what order those go in. I pick one of the triangles, I see an angle, and where's my tick? Not between them, so that again is angle, angle, side. Here's another one that has some right angles in it. I wonder if we'll use the right angles congruence theorem. And it also looks like a bow tie, and so those right angles are actually even vertical angles, which is kind of strange. I think I better mark my givens. I see that it says that AB is congruent to DE. That's a set of congruent sides. It also says that C is the midpoint of AE. If C is right in the middle of A to E, that would mean that AC is congruent to CE. And every good proofer knows that if you see a vocab word in the givens, you're going to use the definition of that vocab word as a reason. So now I have another set of sides. I ran out of lines, but I guess I could squeeze another one in. Is there another set of angles that are congruent? I could say that these right angles are congruent. But wait a minute. If I were to get a set of congruent angles, wouldn't my only choice for two sides and one angle be side angle side? And I don't think that those right angles are the right angles. Do you know what I'm saying? If this were a side angle side, the angle that's marked congruent would have to be the angle that's between those two. Whenever you feel like something's going wrong on a right angle proof, you should always check to see if maybe it's an HL example. Is it possible that I can just use those right angles as right angles and that those two sides were a hypotenuse and a leg? Well, I see that the AB and the DE were the hypotenuses. And so that other set from our midpoint, that we could call that a pair of legs. So this one is an HL congruence theorem to show that those triangles are congruent to each other. Notice that I didn't need to say that the right angles were congruent to each other in order to use HL. So I would only need to use the right angles congruence theorem if I wanted to use that just as a standard pair of angles in, say, a side angle side or something. I brought in some more parallels for you. Remember that I like to look for maybe a Z shape when I see those parallel lines. So if I were to look at the AB and the DC, can I make a Z shape out of those? I think I see one right here. Now the downfall on this one is that the angles that would give me are this angle A and this angle C, and that angle C isn't even in a triangle. So maybe the Z shape isn't what I should be looking for on this one. So let's try again. If I have this parallel to this, what could I use as my transversal? Do I have a line that's running through both of those? I've got AC that's going through both of those, but that's not getting me quite the angles I was looking for. What if I used this as the transversal? If you need to draw it out on the side, I wonder if you can see almost like an F sort of shape going on here. Maybe that's too much of a stretch, but we should have some corresponding angles that are congruent. I can say that this angle B and this angle C are congruent by the corresponding angles postulate. I don't know if that F shape made any sense to you, but if you think it would help, you could write down that F and show that we'd have corresponding angles going on whenever we can see sort of an F shape out of our two parallel lines. So angle B and that angle C used that first set of parallel lines. What can we do with the second set of parallel lines? Again, I could make a Z shape, but I'd be using that outer angle, not what I'm looking for. So I think maybe we should use this as the transversal again and go for the upper angle C and the upper angle E. Those are corresponding angles. And if you're trying to go with my letter analogy, here's the F shape that you would find. Anyway, these two parallels then are going to give us that other angle C congruent to angle E. And that was by the corresponding angles postulate again, and using that given. I've got a third given. Maybe that'll help me find a third set of congruents. So far I've got one set of congruent angles. I've got two sets of congruent angles. I need one more set of congruent, I suppose it'll be sides, right? Because there's no angle, angle, angle. It'll have to be a set of sides. And the clue again is right in the given that C is the midpoint of BE. Are you guessing that definition of midpoint will come up? Let's look at the picture. What does it mean for C to be right in the middle of BE? It means that BC would have to be congruent to CE. I have two angles and a side again, but this time I've got angle, angle, and the side is the one that's right between those two angles. So this one is angle, side, angle. I made another one with parallels here, but one thing I just can't help but seeing when I look at this picture is a bow tie. And what reason do I always use when I see a bow tie? The vertical angles congruence theorem. The vertical angles congruence theorem says that those vertical angles right in the center of the bow tie are congruent to each other. So maybe you even want to draw a little bow tie next to vertical angles on your pink sheet. I can't call those both angle B, so I'll just trace around those corners, like A to B to E for that one, and C to B to D for that one would be just fine. As long as that B shows up in the middle both times. Okay, I dealt with that bow tie. Let's see what we have. We were given one set of congruent sides. We just found ourselves one set of congruent angles. And these are sides, but they're not congruent sides. So what are parallel lines helpful for? Parallel lines help us to get congruent angles. Parallel lines help us get congruent angles. So we'd want to be looking at these parallel lines and thinking, okay, where could I put a transversal? Could I make this the transversal? That sort of looks like an N or a Z if you tip it on its side. On this one, you actually also could use this as the transversal. That's just a Z flipped around in the other direction. So there's more than one correct answer for this problem. The first thing I saw was to use AD as the transversal, so I think I'll stick with that, which would give me angle A congruent to angle D. And what is the reason? It was because of the parallel lines. So if you're looking at your reason sheet, you should be looking under parallel lines and angles. Those are alternate interior angles. And maybe you have a Z written next to those. I left this last little part blank because I want to make sure that you are naming the triangles in the correct order. If somebody calls this first triangle A, then E, then B, I have to be really careful what I call the second triangle. I can't just put them in alphabetical order. I have to use the corresponding parts. So what angle matches up with angle A? That would be angle D. And what matches up with angle E? That would be angle C. And what matches up with angle B? Angle other B. A to E to B, I would need to go from D to C to B in order to trace out the same angles and the same side on this one too. And because I chose angle A and D, it looks like this formation is an angle side angle, since that side that's marked congruent is sitting right between those two angles that are marked congruent. I always get way too excited about shared sides and bow ties, I know, but I can't help it. Why don't I just take the easy point? If they're both having a side BD, I can say that side BD is congruent to side BD by the reflexive property. Then I'll step back and see what else I have. I have this set of sides that's congruent. I just found myself another set of sides that are congruent, and I'm wondering if this given is going to get me a third set of something that's congruent. It could be SSS, or it could be SAS. I'm just not sure yet. But if we look at the clues, it says that segment BD bisects angle ABC. What does that mean? Look at the picture. Segment BD bisects, where's angle ABC? Angle ABC is this top angle, this huge top angle up here. So if BD bisects ABC, that means that those angles are congruent up there. So with BD being a bisector, I would be able to say that this angle B and this angle B are congruent to each other. That's what it means to bisect. So this one gave me congruent angles, I guess because it was an angle bisector, right? Can't call them both angle B, so I'll trace around and put the B in the middle. A, B, D could be that one on the left. And the other one could be C, B, D. And remember, we were using that vocab word, so that's the definition of segment or angle bisector. We were bisecting the angle, so that's an angle bisector. At first I thought this was going to be an HL, because don't these totally look like right angles down here? But it never really told me anything about angle A and angle C, and actually, it looks like that's the thing I'm trying to prove, that angle A is congruent to angle C. I don't know how big they are, but I'm supposed to prove that they're congruent. Now at the start there was no reason that I could put right there, but here we're about to do this famous last 1-2 punch, where we say first the triangles are congruent, and it looks like my formation up here is side, side with an angle between, side, angle, side. And now that we know that those triangles are exact copies of each other, they are congruent in every way, then we know that that angle A from this triangle would have to match the angle C from this triangle, because corresponding parts of congruent triangles are congruent. Or you could put definition of congruent triangles. That's the 1-2 punch I speak of. We use one of those 5 triangle congruence reasons, followed by my CPCTC. Last one, and this is another one that goes past those congruent triangles. Do you see how congruent triangle shows up right here? But then we're not done, and we're trying to prove that BT is an angle bisector, I guess. Let's see what we can do. First of all, my givens. AB is congruent to BC. That's a set of sides. AD is congruent to CD. That's a set of sides. And does this look like a bow tie? No, but they're sharing side BD, so I'm going to say BD is congruent to BD. What property? The reflexive property. And that's a third set of sides. So I wonder, what reason might I use to show that those triangles are exact copies of each other, that they are congruent to each other? It's going to be a triangle congruence theorem. There's 5 of them, right? This one is the SSS, congruence postulate. And what was that thing about the 1-2 punch? What do we always follow our congruent triangles with? The fact that corresponding parts of congruent triangles are congruent. So I'll bet you that this is going to be a CPCTC. I haven't even looked ahead, but I bet that's how it's going to go. Okay, now I better look ahead a little bit. I am trying to prove that angle ADC, that's this one down here, gets bisected by that BD coming right down the center. If we're saying that that ADC angle is being bisected, we're saying that those two angles got cut equally. So is it true that this angle and this angle are the same? Are they congruent? And I would say yes, they're congruent, because if the triangles are congruent, then all their parts are congruent. Those two angle Ds are definitely going to be congruent to each other. So I can say that angle ADB is congruent to angle CDB, and that's by corresponding parts of congruent triangles are congruent. And this one pushes us just one step further. How is it now that if we know that those angles are matchy-matchy, why can we call BD a bisector? Because that's what a bisector does. A bisector makes those two angles congruent to each other. Because that's what a bisector does. That's the definition of an angle bisector. BD is a bisector if and only if those two angles are congruent. That one was kind of advanced, but you made it to the end of the video, so you were ready for it, right? Send me any questions that you have.